All right, so welcome. My name is Kayvon. I'm a pretty casual guy, so Kayvon is a perfectly reasonable way to address me.
Hi, I'm Kunle. I'm the other instructor. You know, Kayvon's the software half, I'm the hardware guy.
Yeah, so I'll be doing a lot of the lectures at the front of the class, which are a little bit more software-oriented, and then you get the A-team in the back half of the class to tell you about how hardware really works. So you're going to have, right now we have 9 TAs, you're going to have 10 or 11, so we'll hopefully get everybody pretty good support. Okay, so I'm a big person on motivation, so I thought that we would start by, okay, so first of all, I like to try and make lectures as interactive as I can for a big class like this. So one thing I'd like you to start is, why don't you just turn to your neighbor, who hopefully is a friend, or maybe not a friend, maybe you've never seen them before. You might be working through a few things with them today, so why don't you turn over, introduce yourself, say hi, suggest that you're a pleasant person to be around, and then one thing is, why don't you tell everybody why you are here? Okay, all right. So hopefully you've. Great. Very good job. Very good job. Okay, so here's a question for all of you. We have 270 people in this class, which is more than we've ever had before. It's always good to know why people got their butt up this morning and decided to take this class. You know, why are you here? This is actually a class where we have pretty different people showing up. We often have hardware architects, we have software programmers, we have people in machine learning that are tired of waiting for training to go. We have graphics folks. So who's here? Why are you here? Yes, sir. Sitting in the front, obviously.
So I did my undergrad and most of my master's degree taking AI classes. Yeah, but I received feedback from people in the industry that
you come slow.
And I think there could be no better class than this class.
I think so. I think one of the things that I'd like people to take away from this class is that computers are a hell of a lot faster than they actually think they are. And so having, especially if you never built a system in your life, I'm not saying that you will, but for folks that are applications focused, I think that having a little bit of an intuition about how fast something should be is extremely important. Like when someone working for you goes, look, this computation's taking all day, you should be like, I mean, I kind of understand what that workload is. That should be a 5-second thing on 10 cores. Can really be helpful. Anyone else? Yes, sir?
Yeah, my mind is like hardware, there's software, and then what's going on in the middle to me.
Okay. Yeah, that's great. So we are going to talk a lot about the interface between hardware and software. Typically, getting that interface right is step one to the key to performance a lot of times. Anybody else in the back? We got some machine learning interests. We have some hardware-software boundary interests. Anybody else? Do we have any graphics folks here? Yes, ma'am.
I'm interested in everything.
Cool. I mean, graphics, like machine learning, has always been this field that's we got to get the algorithms right, but we also got to run really efficiently. So a lot of the technologies that we'll talk about have some genesis in graphics. So, okay. So some of the things that we're going to talk about. This is actually, first of all, how many people have spawned a thread before in their life? And in what class did you spawn a thread for? 110. And you spawned a thread in 110 in the context of what? You're writing the thread pool, okay. And did you, I actually forgot, you wrote the thread pool for what application, or was it just a generic thread pool?
It was just a piece of.
Just a piece of, okay. So you didn't create a thread pool to actually have a concurrent application at all?
Yeah, I mean, we were trying to do like, it was like Stanford Farm or something like that, where we were trying to like run arbitrary prime number method and A4 stuff.
Okay, all right, so you wrote a thread pool for exactly the reason on this slide, which is you wanted to use as many cores as you could in order to get stuff done faster. Makes sense. A number of you have probably also written thread pools for web programming or something like that before, right? Like, has anybody written like a web proxy or a little web server or something like that? A lot of the times we spawn threads to hide latency, to do something else. But in this class, we're going to be talking about multiple uses of why we're creating parallelism. And this class is, even though it's called parallel computing, we're going to talk about efficiency as much as we're going to talk about parallelism. And sometimes efficiency is a lot more important than parallelism. So I like to play a little game in the first day of class just to kind of make some things a little bit more explicit, at least while everybody's here. So who can handle pressure? Got some people. You, name in the back? So would you mind coming to the front of the room? Because there's no bigger pressure than doing something in front of everybody else. And it even gets worse because I'm going to have you do math in front of everybody else. So if it was me, I'd be quaking in my boots right now. Okay. So here's we're going to use you as a little processor. Okay? So there are 16 numbers on pieces of paper right here. And I'm going to ask to just add them up. That's all you got to do. Hold on 1 second, and I'm going to time you. And what we're going to do is we're going to see how fast one person can add up all these numbers. And then we're going to see if we can do better. Okay, so prepare yourself. And whenever you're ready, I'll start the timer, and we'll time how quickly you can add up 16 numbers. So whenever you feel comfortable, go right ahead.
Okay, I'm ready.
Okay, go for it. Timer has started. And I'll be quiet so I don't disrupt.
I think it's 106.
That's very, very close. Close enough, but very, very good. It's a very high-pressure activity. Okay, so you were able to add all these numbers up in approximately, if I I'm going to remove a little bit of time when you were just kind of getting started, but it was about 40 seconds. About 40 seconds to add up all the numbers. Okay, so I'm going to thank you, and we'll keep going with the lecture. So thank you again. Okay. So 40 seconds, and this is our first parallel program of the class. And I might suggest that how can we do better? So one way we could do better is we could practice a bunch over the next couple of days, and we can call back up next week and say, let's try it again, and let's see if we can get those 16 numbers done even faster, right? So she could work on arithmetic tables or something like that. But what are some other ways we could maybe do faster? So obviously where I'm leading you is let's try this with more people, right? So luckily I have sitting here with another set of 16 numbers. The answer is different, so you can't just repeat the same number. And I'd like to have 2 more volunteers to see if we can use 2 people to do better than about 40 seconds. All right. So you seem very confident. Please come on up. Nice. I'm going to put these face down so you can't at least pre-compute some of them. And we need another volunteer. Oh, by the way, what's your name? Okay, so first of all, thank and thank. And I'd like another volunteer, but I in particular want a volunteer from the back of the room. Yes, sir. Okay. So you're going to be working with, your name is? That's great, but I don't want you to go to the front of the room. I want you to stay back here.
Sounds good.
Okay? So you can't look at these things. And what I want to know is I want to know what the sum of these 16 numbers is. I believe both of you have 8 of them. But here's the catch. Somebody give a piece of paper and a pencil, or if you have one. I'm sure we can figure it out. We have 270 people in the room. All right. So you 2 can't talk, but I want to know the total sum. So whenever you're all ready, feel free to grab your pieces of paper. 1 second. Let me reset my timer. And ready?
Just to ask the premise again.
Yeah.
He's getting the same numbers?
No, you guys have different sets of 8 numbers, and I want to know the sum of all 16.
Without communicating?
Well, he has a piece of paper. You can communicate, you just can't talk.
Okay.
Okay? You ready? Go for it. You solved the problem. I'm not, don't look at me. Okay. $112. That's actually exactly correct. And very good. Very good. And I can prove it to you because I wrote 112 right here. So that is correct. All right, great job. Now, how did anybody notice how long that took? My stopwatch says 41.7 seconds. So we had one person that, I gave Tina a little bit of credit because it was actually more like 45, but I tried to get rid of some of the rustling of the papers. But let's call it 45, and let's call 41 seconds. So we have two people, twice the resources, twice my CA budget, and I got, how much better did I do? I did what, like 10% better. So what's going on here? What would we have expected if we assumed that everybody could do math at approximately the same rate?
60% of the time.
Sorry?
60% of Tina stuff.
Okay, why did you say 60%?
Have it and then add it for some resource communication between the two parties.
Okay, and then ideally, like the best we could do, if you had some telepathic connection or something like that, would have been, it should have been about 2 times faster, right? 2 people, twice the resources, 2 times faster. But we actually basically weren't faster at all. And so what caused that? Did anybody notice how long it took the second group to do the math? It actually was at about 21 seconds when you started throwing up your hands, going, I'm not sure what to do next. And I think it was like 23 seconds when he finished his math and started walking towards you. So what was the deal? Yeah.
The communication between the two.
We had to do some communication. So this is actually a problem that is pretty trivial in some sense to parallelize. But just something as simple as getting one number from one side of the room to the other significantly blew up all of our speed up immediately, right? Like like we had students twiddling their thumbs. Now, if I gave you the opportunity to do it again and you could sort of do whatever you wanted, how would you maybe speed things up?
I would walk over to him while adding the numbers.
Okay, so we could walk towards each other while adding the numbers. We can sort of start communicating essentially while we're still doing the math. What if I gave you other rules, like you could yell or you could use WeChat or something like that?
I would use WeChat.
Yeah, so there's some way, like if we could shout, or if we were sitting here on WhatsApp, like we could reduce the amount of communication significantly, right? So what we saw here is something that, I don't even have to prop this equation up on the slide, right? That's pretty obvious to everybody. I said, what should the speed up be with 2 people? And you all were like, well, it should probably be about 2x. And we got that speed up for the time for one person, the time that Tina took, divided by the time using 2 people, or in this case, p equals 2, right? And the observations were that it was really this minimizing the cost of communication would actually be the hard part of trying to use 2 people under these conditions, okay? So if 2 people is hard, maybe we should try 4. Okay, so luckily I have 4 groups of things set up. So I'd like 4 volunteers. And so first 4 people to come enthusiastically run to the front of the room will get to participate in this activity. Okay, so here's what we're going to do. I'm giving you all some work. You each have your things. Can start. And so, ideally, now you're all right next to each other. And, I'm fine with allowing you all to talk.
Okay.
Like you all talk. You're all right next to each other anyway. I'd like to know how fast you can do this. And we expect, maybe on the order of 12 seconds or something like that if we're in good shape. So let's give it a shot. So we got 4 workers. Go. So what happened here? What do we observe? What was first of all, what was the reason why this didn't go very well?
I got a lot of numbers.
You got a lot more work than everybody else. I also give you bigger numbers just to make it a little harder.
Oh, okay.
These people were adding up like 4 and 5. and so, okay, so why did that affect the speed?
Because my latency was higher than the other people. I took more time because I had more work and the work distribution wasn't equal.
You had more, yeah, you had more work, so everybody else was waiting for you, and they didn't have anything to do. Okay, so I'm gonna, unlike the other folks, I'm gonna give you all another shot.
Okay.
Okay, so I have a different group. Now, in this case, I do know it comes out to, I think, the same side.
Hey,
But
Kayla.
I'm not going to make any guarantees at all. Okay, so I'm going to redistribute to everybody. Now, before you do your work, why don't you all talk a little bit about how you're going to do this? And with your friends over there, I'd like you all in the audience to come up with a scheme about how you would do it if you were standing up here trying to coordinate 4 people. And there's a number of different strategies. So I'll give everybody like 45 seconds or a minute to talk it over. If you were up here with 4 people and you had no idea what were in those piles, how would you do this?
I think I'd go first. Maybe if you have...
And feel free to talk about it in groups.
Yeah, just to give it to
Okay. I think that's enough planning time. So take your packets. And 1 second, let me get ready. Are you ready? Go. Okay, I'm looking to see what they're doing. I'll explain it to you in a second.
34. This 34. 64. 35. 64 plus 35 is 26. 99. 99 plus 26 is 125.
You're off by 10, but that's fine. 10% error.
Not to be used in banking.
It was 115, but whatever. Sometimes we don't check correctness on assignments. Okay, so you did it all. They did it in 19 seconds, and I think things are a little bit occluded. Why don't you summarize to the crowd how you did it?
Yeah, we just once we got our packets, we just put them all in like one big pool, kept taking and adding, and then once all the packets were gone, we just kind of added them all together.
Yeah, so everything got thrown into a big pool, and then everybody just took the next available thing as they were adding. That was their scheme. Now, it might, you would have run the risk of maybe you would have bumped into each other's hands or something like that, but actually that didn't seem to be the case. And the reason why that didn't seem to be the case is that, by the way, that took 19 seconds to do. But at 12 seconds, all of you had finished your individual math, actually. So you almost were perfect up until there. And then it took 7 seconds to add up the partial sums. So your parallelization scheme was actually executed quite well. So anyways, thank you to the group. Did anybody else in talking over? I mean, there's a number of ways people could have done this. Were there any alternative schemes that were devised in the crowd? So again, the scheme here was throw everything into a pot and take the next thing out of the pot.
Yes. I think we forgot to do one thing there. Once all of us added our numbers together, I think we planned this, but we didn't do it. 2 of us should have added it together first, then the other 2, and then together.
It is true. You all kind of waited around until all the partial sums were done, and Yep. I bet you could have shaved off 2 or 3 seconds if you did that. Any other strategies in general? Let me just go on this. Yeah.
You could distribute it into 4 pools beforehand.
Right.
Like
Yeah, so another way would have been just anybody that had more than 4 pass to people with less than 4, get 4 to everybody, and then do the work. Mm-hmm. Now, in practice, they ended up probably with about 4 items per person just by grabbing the next. And what if one of the students would have been just really bad at math? Or maybe one of the students got some numbers that was very, very large and harder to add. So your scheme, which is great, and actually the one that I anticipated them to use, was redistribute all the work up front, do things independently, and then come back together. What they chose is they actually decided to just sort of sync up constantly by taking the next thing. Mm-hmm. Any other strategies? No other strategies?
we were thinking of using like a thread dispatcher to have one person who's just waiting and ready to sum the other three partial sums. So one person stands okay. The other three are summing, and then as they come in, the fourth person just sums.
So you said you could have one person holding the total sum in the head. Okay, that would actually potentially work. Now, what's the cost of this scheme of using 3 people to add up the numbers and 1 person to do the other ones?
If there's like a lot, there's more than 16 numbers.
Yeah, you're basically letting someone wait while everybody else is doing work. Now, in practice, I think your solution might have worked quite well because that person was waiting for a very short period of time. And it's only 1 person waiting for a short period of time, whereas what they had at the end were 3 people waiting for a short period of time. Cool. Yeah, makes sense. Any other comments? Ways of going about this? Yes.
Yeah, can you explain the thread dispatcher?
Well, the scheme was we're going to let one person just stand off to the side and do nothing. And that person will recognize when the 3 other workers got done with their partial sums. And that person is only responsible for adding those up. Right? So they can presumably they can start adding numbers up in parallel with the long worker. So another possibility. Seems perfectly valid to me. Okay. All right. One more before we get on to some class logistics. And this is the more interesting one that I want you all to decide as a class. What I want to know is how many people are in the room right now. Okay, so I'm going to give you 1 minute, minute and a half to talk it over with everybody else. As a class, you need to design a strategy for how you're going to do this. And I'm going to put the timer on you. And we're going to try and estimate how many people are in the class right now. Let's say there's 150 people in the class. If we can do 16 numbers in 45 seconds, or round up to a minute, well, that means that we should be able to do the whole class of like 160 in 10 minutes, right? Divided by 100 people, so this should be just a few seconds to add everybody's up. Yeah. So how are you going to do it? Okay. All right. So let's come back together. Let's make sure we have agreed upon a scheme. Have we? Have we converged to an algorithm with 150 people in 90 seconds? Someone be assertive and say, here's how we're going to do it.
Count the number of rows, count the number of people in each row, and add up the rows.
So that's what you're going to do?
Back of the room.
Is that the plan? Yes. Anybody want to, that's a perfectly fine plan. Does anyone want to add anything to it?
Also split the rows in sections, so this section goes separate and that section goes separate.
So we're going to add up, is that the plan? 1, 2, 3 separate?
Every row in every section adds their row, sends the sum backwards, and then the back row amalgamates all 3 of the sections from the outside.
Okay.
The one?
Are you sure? Because I feel like there's a lot of the class that's going to be sitting around.
What's not ideal here is that the back of the class is not doing any work while we are working here.
Yeah, the back of the class is going to be doing a lot of waiting while this partial sum is rolling back. Anybody want to?
Start at the back and some meets in the middle.
Okay. Okay. So there's a proposal to start in the back and push forward, and start in the front and push back, and you all somewhere in the middle are going to have to produce it. Does that sound okay? Any more? Yeah.
Maybe one person or 2 people, one front of the back, like count the number of people in the back, and another person count the number of people in the front, and then combine that, and then send it to the other section in the middle.
I see. Sorry, I didn't quite get it. So are we still doing rows first?
For the front section of front rows, and then another person for the back rows.
Okay.
And then combine that.
But how's that? So only 2 people are going to do the work?
Kind of observing, yeah.
I think I know what you're saying, but I'm not sure if I can translate it into pseudocode for 150 people in 10 seconds. But okay, one more thing, and then I think we're at a scheme, and let's just see how well it goes.
Yeah. Well, everyone tries to group by 10. Each one finds a group in 10, and finally we just count how many 10 groups.
Now we're doing something different. So the proposal is get your butts up, get into groups of 10, and then count the number of groups. So, who wants to? Is there a strong feeling?
Yeah, that one's
I think people want to move around. Yes.
You have everyone sit in the middle row.
Everyone sit in the middle row.
Everyone fill up the rows. The first row.
Oh, okay. The other thing was everyone pre-compute the number of chairs per row, and everybody fill up the front rows and count the rows. Okay, I'm gonna get one more. These are actually a lot more creative than previous years. So,
Good.
yeah. What's
So you have one person post a poll on Ed.
Yeah, that's a good idea too, right? I think you could probably do that one in parallel with the in-person algorithm too, and see which one converges first. Sometimes it's called speculative execution. You do two strategies and you see which one wins. Okay, so which one do you want to go with?
Filling up rows.
All right, filling up rows?
Yeah.
Okay, are you ready? 1, 2, 3, go. Didn't expect that.
I was.
All right, we're at 2 minutes. 10 minutes is a serial algorithm.
12, 16, 24, 30, 36. Yes.
All right. Just do the poll on Ed. All right, about 2 minutes so far. I think if we... I like that perseverance.
There's 45 in this section.
All right. I think just for the sake of finishing the lecture, first of all, I actually think this is a very creative solution. I thought all of these solutions were going to work pretty well. This has never been proposed, I think, in my time of the class. And the groups of 10 also have never been proposed ever in the class. So what do y'all think, actually? So let's maybe do a little bit of a post-mortem here on what was good, what was bad about this. Yeah, what was good?
I think there should have been like 1 or 2 people that are just dedicated to counting everyone while they're being seen.
I do have a feeling that this idea of just separating somebody off to the side to be responsible for counting, given this number of people, probably would have been helpful. Yeah, exactly. I have also a feeling, which will be somewhat embarrassing, that if your algorithm was one person, just count everybody in all the rows, they probably could have done it in 2 minutes. What else did you notice about this? Yeah.
I think like we need a lot of communication saying that, hey, do empty here, that kind of stuff.
Yeah, so you kind of had like an allocation problem. You also had a big data movement problem just to get everybody into the appropriate seats. So I actually think in hindsight that groups of 10 might have actually gotten people to a countable set a little bit quicker because you didn't have these dependencies to get everybody in rows. So I have a feeling that like if you're getting hot and things like that, why don't you file back to wherever you feel most comfortable. But thank you very much. So if I assume there's like 160 of you here right now, that was like only 10 times more work than we originally asked to do, for example, right? And so it shouldn't have been more than about 6 or 7 minutes to add it all up sequentially. It should have been much less because now it's just +1. It's not adding a harder number. But we were nowhere close to that, right? Like in terms of a 100x speed up over the sequential algorithm. And it was largely because of the cost of communication, synchronization, moving all of you. And so this is something I want you to keep in mind because although the class is about parallelism, I mean, the reality is that it's really about moving things around. Like every system that I think I've ever built, I bet Kume probably would agree, is kind of the only thing that really matters is communicating and moving stuff around. Okay, so let me get into just some summary and some logistics real quick. Theme number 1 of this course is we're going to get you thinking kind of like you were just thinking now. Like we're going to give you problems. You need to compute this problem, and you need to do it as efficiently as possible. And so we're going to want you thinking about how to decompose things in parallel and how to synchronize. And we're going to, I like that there's some folks interested in the hardware-software boundary because we're going to talk about programming mechanisms that help you organize that thinking, that make it a little bit easier to solve problems like this. Now, some of you are computer scientists, your day jobs, or you write software. Some of you are EE and design hardware. Another aspect of this course is about the fundamentals of how hardware works, because you can't make things go fast if you don't know how things are running under the hood. So the hardware is a little bit about why code has to be structured in certain ways in order to run fast. So software people, hardware designers need to know about hardware because they like to build this stuff. Software folks need to know a little bit about hardware to go, wait a minute, why am I making my program structured this way? It seems hard or it seems difficult. Why can't I write it in another way? And more so than in previous years, there's going to be a stronger component in this class of actually designing hardware itself. So there may be an extra credit assignment at the end of the quarter where you can actually make a piece of hardware on an FPGA or some programmable substrate. And then the last thing I want to just really emphasize is I care a lot about teaching people about efficiency. In some cases, like in this exercise where we added up the number of people in the room, if it would have been easier for one person just to scan the rows and add them all up, that's great. That's a faster, potentially more efficient solution than a solution that was highly parallel but had a lot of communication. So let's not get too hung up on parallelism, because efficiency is often what matters. So here's an example. Imagine that you go off to your next internship or full-time job or whatever, and you were asked to write, to speed up a program on a 10-core processor, something like that. And you came back a month later, and you were able to get 2x speed up. You went to your boss, you said, look, it's 2 times faster. Do you get fired? Or do you get a raise? Okay, so we have a very negative class. Some people want to fire you. What's a rationale for getting fired?
You had 10 processors, but all you could achieve was a 2x speed up.
You had 10 processors, you only got 2x out of it. Maybe you're using those processors very inefficiently. They say, you're fired. Go back, take CS149. Any reason to give the person a raise? Yes, sir? Yeah.
I'm just saying not all programs are like so easily parallelized.
Like the one we just did, right? Like that's a pretty hard program to parallelize. Is there a reason why you might be satisfied with 2x?
Yep. Yeah, if the performance gains by that offset the additional cost of using a 10 processor computer.
Yeah, like maybe computers are cheap, and like being able to reduce the response time of your website by a factor of 2 translates into a ton of sales. You might be really happy. Or like Google search results have to be returned in a certain amount of time, otherwise people lose interest and go somewhere else. Another example: imagine you had a computer game that ran at 15 frames per second in a game, and you made it get to 30 frames per second. That might be the difference between the game shipping or not shipping, right? So sometimes we care about raw performance. Sometimes we care about efficiency. Ideally, we'd like to have both. Okay. Okay. Yeah, and hardware designers care a lot about efficiency, because they're like, the more hardware we put into the chip, the more expensive this chip is going to be to manufacture. So I'd like to put in the minimal amount of hardware that I can get by with and still meet my performance goals. Okay. All right. Middle of the lecture, let's take a breather for a second and just go through some logistics. This would be a good time to ask any questions about logistics. Getting started is that all information on the course will be via the website. So CS149, here's the website. All the lectures are posted. So we try and make sure that your lecture slides are posted prior to lectures so you can follow along while you're in the classroom. Notice that there's a mechanism to comment under the slides. So you can add a comment. And typically, the reason why we do this under the slides is you can ask an actual question specific to the slide. So like intellectual questions, like I didn't understand this, can someone explain multi-threading? Very much prefer them to come in via the slides so that other people can see them and respond, as opposed to making those on Ed. Ed is for like logistics and stuff like that to me. And you can always go up here to the course feed and see all the comments that people have made. Okay, back to my lectures. So that's that. There's no textbook. The slides are basically the textbook. The internet is full of great resources, and so a great way to make a helpful comment would be to say, hey, I actually learned it from this website. The explanation in class was pretty bogus. This is way better. Go read this, right? All right, so you're going to be doing 4 programming assignments. It's the bulk of the grade. The first programming assignment will come out on Thursday. It's a little shorter. The next 3 are significantly longer. You will be writing a much more elaborate version of a thread pool where we give you dependencies and everything. You're actually going to be writing a renderer yourself that will make pretty pictures via CUDA as fast as you can. Not made yet, but intended to do so. Assignment 4 is definitely very new this year. You're going to implement the transformer module of a DNN, and you're going to try and do it as fast as possible so that you can have a chatbot kick out tokens, and maybe we'll have all the chatbots chat with each other or something like that. Okay. So there's 4 assignments. Typically after Thanksgiving, we release a 5th, which means you can use the 5th because it's awesome and fun, or you can use the 5th to boost the score of one of those by a few points, usually about 10 or 15 points. Okay? Most of your grade is there. We do written assignments that are graded on a did you make a reasonable effort. The written assignments are all previous year's exam problems. So about every 2 weeks, there'll be a written assignment plus practice problems. So we distribute practice problems throughout the quarter. You can think about this as a participation grade, largely. And then the last part of your participation grade is I do not want people studying for the final exam and not thinking at all about the course between now and the final or the midterm exam. So just to force you a little bit to engage with the lecture in the same week as the lectures, we require 1 reasonable comment per lecture, approximately, in approximately the same week as the lecture. So no hard rules on this. But I hope that you average about 2 comments per lecture throughout the quarter. And if you really like a lecture and want to do a bunch of comments on one lecture and skip the next lecture that week, that's fine. But no, it's not cool to do 35 comments when you're studying for the midterm and only then. Right? And so you can kind of see some of the interaction that happens. Like these are real comments from students before. And so we expect you to do that. And I think good architects typically write well, write clearly, not elegant English language prose, but as an architect, you're constantly communicating to other people about technical things, and I think this is a very useful thing to be doing. So you can take this offline, but here are some examples of fodder for comments. In a big class like this, the comments actually works pretty well because somebody asks a question and then other people answer it. Don't worry if someone has already answered the question. You could answer it again in your own words or something like that. There are a bunch of ways to interact. A lot of people post cool links, like I saw this on Stack Overflow. It's a great example of this concept and stuff like that. Grading distribution is here. So 58% programming assignments, that's most of it. Exams are about 30, and then these 2 participations are just like last year, about 10% of the grade. Okay. The only last thing I wanted to say now is we do 8 late days per quarter. You can use your 8 days for programming assignments or for the writtens. Most people use them for the programming assignments because the writtens are just participation. That's pretty generous. That's 8 days throughout the quarter. So we expect that those late days are for most life situations. Minor illnesses, getting busy in other stuff, taking athletic trips and things like that. I was a college athlete myself, so I understand and I'm sympathetic. But I think that the 8 late days should handle most cases without asking. If you get yourself in a situation where this is going to be trouble, come talk to us in advance. I mean, multiple days in advance. You're like, I foresee this, me not being able to complete my work. We'll handle it on a case-by-case basis. But I bet 95% of the time, I'm going to say, just use your late days. That's what they're there for. No problem if you turn in your assignment 3 days late. I think we have a rule that programming assignments, written assignments can only be 1 day late because I want to release solutions and they're for credit only. Programming assignments, I think, can be up to 4 days late. I can't recall what it was on the website. It's 3 or 4. Okay? All right. Any questions about logistics? That's all I was going to do about it. Yeah.
One, not a question, but kind of feedback. Like in both the programming and written assignments, could you indicate like which question or which component could be completed after which lecture?
Sure. Yeah, I could even do that in lecture. I mean, it's not super modular like that, actually, so it might be a little hard. But in general, the programming assignments, with the exception of assignment 1, all the content, I believe, is released prior to all the lecture content exists prior to the assignment coming out. In assignment 1, you'll have conceptually everything you need on Thursday, and logistically with a little bit of programming example comes next Tuesday. But yeah, yes.
Will the final exam be in person?
Final exams in person at the university slot. That is the one thing that we are a little bit strict on. It is hard to run asynchronous assignment. So if you're an in-person student and don't have an extremely, extremely strong reason, we expect butts in chairs during the exam slot. Okay, so I accidentally bought a ticket to go home early. Don't accidentally buy a ticket to go home early. We've actually accommodated them in the past, and it just makes for a mess in the TA grading, and then you never know if the solutions get out and stuff like that. Okay, yes, ma'am?
Get a code to make an account on the
Yeah, sure. I just wanted to double check a few things before I had everybody sign up. Yes. Yep. Mm-hmm. Okay. All right. So keep going. All right. So the last 20 minutes here, 25 minutes, maybe let's go into a little bit more technical material that is perfectly fine if it's new to you, but some of it may be stuff that you have seen. So I like to set the stage for tomorrow or Thursday's lecture. Okay, so sometimes it's kind of useful to think historically about things. And when I was approximately sitting in classes like this, and I was really interested in parallel computing, I actually had professors tell me, why are you interested in parallel computing? Just wait a year for processors to get faster. Right? And so this is a very old plot that Kunle made more than almost 20 years ago now. Of processor performance as a function of time. Okay? And it's a log plot, so you see the exponential. And so you just waited, and Intel would ship their next CPU, and next year it would run your program faster. So you spent all this time taking CS149, you got some skills, and then all of a sudden, your parallel program had to now be even faster to improve over the sequential program. And do you know why that was the case? If we maybe some of the hardware architects in the room? Yes, sir.
Transistor sizes getting smaller.
Transistor sizes were getting smaller, but that's not a direct translation to performance. So you're correct, but you took a couple steps. So transistor sizes getting smaller allowed for a couple of things. It allowed for them to be clocked higher, so frequency could go up. It also meant that more transistors could go on the chip, and architects had to have clever ways to use those transistors to translate into performance. Okay? And in this class, I'm oversimplifying a little bit, but you can kind of think about two major reasons as parallelizing your code for you without you ever knowing it, and two, increasing CPU clock frequency. So this is where I get to a few questions that may seem really dumb, but one of the reasons why I like people writing comments is sometimes when you sit down to write something, you realize that your thinking is not as precise as it may seem. So, look to your left or right, and I want you to spend 30 seconds answering this question. What is a computer program? From the perspective of a computer. Here's definitely a program written in C. No problem. This is a computer program. But from the perspective of a computer, what is this? What is a program? And just go ahead and give that a shot. Spend 45 seconds. What is a program? Can you define it yourself? All right. So someone who hasn't said anything yet, if a talk show host found you on the street while you're walking around San Francisco and they said, "What is a computer program?" You're on camera. What might you say? I just want to see some new hands. New hands. What is a computer program?
A piece of text that can be translated to hardware instructions.
A piece of text. That's a piece of text. That can be translated into hardware instructions. And I think that the text aspect doesn't really matter too much. What's important is the back half of your comment is a program is just a list of instructions. Right? So if I take this program, it certainly has a meaning. It has some semantics, and a compiler might get to it. And at the end of the day, Whether or not it's a compiler or interpreter doesn't matter, but at the end of the day, a computing machine runs a list of instructions. So here are some examples of x86 instructions that you might have seen. So in CS1, 11, now like folks, so 7, you've looked at a bit of assembly. This is x86. Most, if you have an Apple laptop these days, it would be ARM assembly. But at the end of the day, all a computer does is it gets a list of commands and it executes those commands. So it's kind of like me making carne asada, which I have to make tomorrow night because I'm out for dinner. I get a list of instructions. I have a set of commands, and what do those commands do? Or maybe another way to ask this question is, what does a processor do? So I'll throw it back at you. Talk it over for a second. If I asked you and I said, what does a processor do? If a program is a list of instructions, what does a processor do? I'll let you talk it over for a second. And for those of you that just said executes the instructions, which is a perfect first answer, my follow-up is, what does it mean to execute those instructions? What does executing an instruction do? Okay, let's talk about this. So I heard a lot of people immediately say a processor executes instructions, which is exactly where I wanted you to think about it. And now let's dive a little bit deeper. What does it mean to execute an instruction? What does executing an instruction do?
Either performing a computation in the ALU.
Okay, so it performs some math, like what you did when you came up here. Okay.
Or it jumps somewhere else in the program set.
Okay, or it jumps somewhere else. Okay. Anybody want to add? I think I can't disagree with any of those. Those are two examples of instructions. Changes a register's value. What are other things instructions might do?
Access memory.
Might read or write to memory. So at the end of the day, we can boil all of this down to instructions perform some operation, like arithmetic or math, and the result of those operations is a change in state. And what I mean by state is either values in memory or values in processor registers. So if I go back, let's look at this instruction sequence here. Oops. Oh, there it was. You see some instructions which are referencing registers, and like moving a value from one register to another is changing the value of the target register. There's other instructions in there when you see the parens. Those are accessing memory at certain addresses and stuff like that. So what I want you to think about, this is a diagram I'm going to use heavily throughout the rest of this lecture and the next lecture. And this is a really cartoon diagram of how to think about a processor. But for most software people, this is pretty sufficient. I like to think about three pieces of blocks in any modern processor. One of them, which I'm always going to color orange throughout this class, is about control. Figuring out, like it's managing where we are in the instruction stream and figuring out, once I get the next instruction, what do I do? Then I have this yellow box, which is responsible for the arithmetic, maybe adding some numbers or carrying out a move or multiplying some numbers. And I'm always going to call that yellow. And then I have stuff that's blue that's state. And I'm calling this the execution context. It's the context in which we run a program, which is just a big set of values of bindings from register 1 has this value, register 2 has this value, as well as memory has all these values. And the simplest possible way to think about a processor is it determines, given where we are in the program, where we are in the recipe, what to do next. It grabs the appropriate values from registers, it performs some math, and then it updates the value. For example, if I have a simple instruction like add the contents of R0 and R1 and put the result in R0, well, that processor will reference the two, R0 and R1. See how it's in red here. It will do the math. It will compute what? Yes, and what is that? Compute 96, and then it will update the value of, so it gets the contents of those registers, it updates the value, and then it modifies the state of the program to 96. Very, very simple instruction, add. And so for now, I want you to think about this processor as every single clock tick. It's just grabbing the next instruction, executing it, and updating registers. That's all it's doing. Okay, so my review here is hopefully this is review from 107 or 111, is what is a computer program? It's just a list of instructions. What are instructions? They're commands, they're operations to the processor. And those operations are about performing arithmetic or modifying state. And when we talk about state, I'm talking about the values of data in registers or in memory. Okay, there's a question?
You answered it.
Okay, cool. Mm-hmm. Right? So this program has 5 instructions in it. So it will take 5 steps, 5 processor clocks to execute it. Make sense? Is there any way we could do better? What if I had 2 processors? Okay, this is your program. This is what, let's say I'm a computer and you hand me this program to run. What does this program mean? This program says you must do instruction 1, then you must do instruction 2, 3, 4, 5. That's the order. If I like trying to make my carne asada and I do things out of order, I will be unhappy with the results, right? So the meaning of this program is that the results have to be such that we did these things in this order. But what if we had 2 processors? Yeah.
Do you want to multiply steps in parallel and not the add steps in parallel?
Yeah, so...
Or maybe not the add steps.
So you're looking at this and you're realizing that like this multiplication only depends on register 0. This one only depends on this value R1. So, maybe if I wanted to assign work to processors, I could do something like this. Right? And now what can I do next? 3 can go where?
Either side.
Actually, it can go anywhere, right? I'll even put it here because I like processor 2 better. And then what?
Add.
Can I do better?
It can go up.
Right? Because this only depends on 1 and 2, so we can do... And then 5 has to come after 4 and 3. So it's possible for me to do better, even if, even if I have a program that looks sequential because it's written in a line. If you look carefully at it, there's some parallelism there. So the first major, and by the way, you notice what I'm saying is the program says, here's the program. You better compute results that are the same as if you ran them in the order that I told you. But if you run them in a different order and I can't tell the difference, then it's okay. And that's a really big difference. This program that I have right here is a sequential program. I have written this program which says the output that I want is as if you did this, and then this, and then this, and then this. I didn't think about parallelism at all when I wrote my program. But I wrote a program where someone can muck with the order, in particular make it parallel, and I'd get the same result. I would never know. But my program would be faster. Right? So for example, what if we had 3 processors? Could we do better? Well, before, what did I do? I did it in 3 cycles. If we have 3 processors, how long would it take? Are you sure? Why 3? Well, I can definitely parallelize the first 3 operations all I want, but I have a chain of dependencies that keeps things 3 cycles. Yes, sir?
So doesn't each processor have its own, in this example,
I'm speaking very abstractly right now. Just imagine that we have the ability to execute 3 things at once, and I'll come back to that in 1 second. Good question. Right? So conceptually, when I look at my program, and that instruction sequence that I gave you, actually, I'm just rewriting it now as something that may be a lot more familiar, like a dot product between 2, 3 vectors, key machine learning operation. These are the true dependencies, and this program has different amounts of parallelism at different points. Okay? So this gets to key idea number 1 today, we've had a few key ideas today, but it gets to the reason why more transistors did translate into more performance, which is processor architects were designing hardware that were looking at the programs that you gave it and said, they didn't do any parallelism, but hey, look what I found. I happen to have multiple instruction units that I can do multiple things at once. I will go find it, and I will reorder the program to be parallel for you without looking, without you ever knowing. And so to your question about registers and stuff, really what I mean here is we replicated, we still have one core, but we have 2 execution units and ability to execute 2 instructions per clock now. And I added this out-of-order control logic box just to say that now there's some smarts on the processor to figure out what's going on. And if we look back like 20 years, you look like for a simple Pentium 4 processor, this is a diagram from a long, long time ago, and I draw my color scheme on it, it's not all that different from my little cartoon. They have the ability to execute up to 4 different instructions at the same time, or 3 instructions at the same time with a variety of units. And real programs are a lot more complex. Here's a longer instruction sequence. A good thing to do on your own is to kind of verify that this is the dependency graph for that instruction stream. And that dependency graph is limiting the total amount of parallelism that you could ever find with this technique of automatically parallelizing within a single processor without you ever knowing it. Yes?
To understand better how that actually happens in the processor.
Well, superscalar execution is the first one, and then you need a good reordering algorithm. You could start with Tomasulu's or something like that. I don't know if these days if that's the best.
Yeah, I mean, basically out-of-order execution is the key.
Yeah, go to Hennessy and Patterson, read the out-of-order execution channel, and then you're well prepared for EE280. But there's a problem. Remember when I said if we had the ability to do 3 things at once, we ended up in the same performance as 2 things at once? That's because if I write just like a sequence of instructions, there kind of usually is fundamentally an order to it, right? And so folks studied, here at Stanford, actually, in the early days of parallel computing, they did a lot of studies of how much parallelism could we automatically extract if we asked the programmer to do nothing and we found what parallelism exists in their program. And they found that the x-axis here is the number of operations this processor could do at the same time, and the y-axis is the speed up. And they found that, once you build about 3 or 4 operations at the same time into your processor, if you start building more, you can't use them because programs don't have that parallelism. Okay? So all of a sudden, they could stop. They couldn't play this trick for you anymore to speed things up. Okay. All right, so here's a graph that you probably would have seen. Again, it's x-axis it's a fancier version of Kunle's old graph. Of x-axis is performance. X-axis is time, and the y-axis is actually transistors, not performance. It's transistors per chip. And in general, okay, now we're starting to fall off of it for the last 5 years or so. But in general, we've been able to shrink transistors for pretty reliably for up until very recent times. Like more and more transistors. Like a modern NVIDIA chip has something like, I think 100 billion transistors on it. I think it's like 85 billion was the last one. So, but we can't turn those transistors into more execution units because we know we can only do about 3 of those things. So that's sort of this green line. This green line is transistors per chip. The purple line here is operations per clock. And they stopped adding operations per clock because it didn't help anymore. Now the dark blue line, correlate both blue lines are actually, they were increasing clock speed, like 500 megahertz, 750 megahertz, gigahertz, 2 gigahertz, 4 gigahertz. And that's what really stopped moving about 15 years ago, right? And for the architects in the room, do you have an idea why clock frequency stopped? Yep. Because of power, right? So we couldn't turn more transistors into free parallelism, and we couldn't make your instruction stream go faster because we couldn't increase the frequency of the machine, right? And that's completely power driven. Like these processors that you see today are non-trivial. Like if you take an RTX 4090 GPU and you take the microwave in my kitchen, you are within a factor of 2 of running that thing, in a machine learning workload at full tilt. Versus microwaving your yesterday's hamburger, you are in the same ballpark of energy being spent. And that energy translates into heat. Heat translates into the need to cool that thing. And so you just cannot continue to increase frequency. And we'll talk a little bit more about that. But a nice rule of thumb is that power is going to go as the square of frequency. So x-axis here is clock speed. Y-axis is power consumption. So it's a very inefficient way to go faster is to try and increase that clock. Okay? So this is where we were not so long ago, when I was in grad school. Software, all of a sudden, the only way to use all these transistors would be I, as the programmer, have to tell the processor, here are two things we can do at once. Now, luckily, in machine learning and computer graphics and image processing and photography, that's going to be pretty easy. And so that's when people started building processors with chips with a bunch of processors in it, where they took that one single instruction stream and allowed for more and more things to go in parallel. So one of the things you're going to do in this class starting on Thursday is the first thing is you're going to go, wow, if I actually just write code properly on a machine that you're used to, like a laptop or the quad-core Myth machines, the difference between C++ code, compiled C++, I'm not talking about Python or Lua or anything like that, compiled C++ and well-written, properly parallelized C++ is about 30 to 40x on your laptop, even with 4 cores. So we'll talk about why that's the case next time, right? And you're just seeing some big chips out there. Like you can go buy an AMD chip these days with 64 cores in it. We'll talk in the class about how NVIDIA processors are more of the same thing, just a little bit different point in the design space. There's 18,000 floating point multipliers on a 4090. So that's a lot of parallelism you have to have in order to use this thing. If you look at how many cores are there in the world's largest supercomputers today, these are megawatts. These are basically power draws of small towns. And we're in the orders of hundreds of thousands of CPU cores. This is not just a big iron thing. Go crack open your iPhone or go crack open your favorite Android phone. You'll find multi-core processing, both CPU and GPU. If you're working embedded, you'll find multi-core processing. All right. So last thing in the last few minutes. So far we've been talking about parallelism and communication and stuff like that. In this class, it's not enough to be parallel. You got to be efficient. And one thing we're going to talk about in multiple lectures this year is how the architects of the world are saying we are not going to, if we have to be more efficient, we cannot provide you general purpose cores. We're going to have to provide you much more specialized cores that do specific tasks. So here, again, this is that iPhone, and now I'm highlighting some of the stuff down here. On this processor, there are 6 CPUs, 2 of which are big CPU cores that are really good, or are supposedly good at running single threads. There are 4 small CPU cores that are lower power and good for background stuff. And then there's a whole bunch of stuff on there for camera, neural networks, sensing, your heart monitor, all of this other stuff that's never even run on the CPU. It's run on specialized processing. That's true in the small. It's also true in the large, with Google building TPUs and Facebook announcing that they're building their own neural architectures, as well as in the Valley these days, the large number of companies that are building special purpose processing infrastructure just for machine learning. So we'll have lectures about all of this throughout the course. Okay. All right, so I'll close up on the thing that I think is perhaps the most important. As you saw when you're walking around the classroom, moving data to the right place is going to be the most important thing we talk about in the class. When you think about parallelism, you're going to be thinking about what do I do at the same time and how do I get the data there? Okay? And here's some examples. So this is where I need to bring up memory, a term that I've used without defining so far in this lecture. So I've asked you what is a program. I've asked you what is an instruction and what does a processor do. And at some point we've said things like a processor issues instructions that modify state. And I said one of the aspects of that state could be values in memory. What did I mean by memory? Like what is memory if you're a programmer?
RAM. Or
RAM
caches.
is an implementation of memory. Like when I look at my x86 code, when I say store this value in memory, I'm not saying it's stored in DDR4. I'm not saying it's stored in on-chip HBM. What am I actually saying? Yeah.
It's like a scratch pad where you just specify the address, and it's a byte.
At the end of the day, all memory is, logically, abstractly, is an array of values. If you give me an address, memory will provide you the value stored at that address. We haven't talked about how memory is implemented. In fact, we will. But I have not told you how it's implemented. So here's an example of that abstraction. I have a table of addresses. In this case, they're referring to the address as the address of a byte. And for every address, there's a value in memory. In this case, I've given you some values that are bytes between 0 and 255. Okay? So memory provides the abstractions that the byte stored at this address has this value. And a load and store to memory, let's say if we're just talking about byte size loads and stores, it says the address at this, the value at this address needs to be set to this value. That's all memory ever is. So a processor has two places where it can store values. It can store values in its registers, and it can store values in memory. And there's example of an instruction might be move the value from memory into a processor register. So I say, go ahead, hey processor, take the value stored at this address, which happens to be 42, and move it to a register, for example, register R0. And what's the effect of that operation? How will my state change? How will the state of this program change if we execute this instruction?
R0.
Yeah.
R0 will have what value?
42.
We'll have 42. It says go ask memory for the value at 42, and you get it exactly. So I didn't show the update. Okay, so you should think about a processor asks memory for information and memory provides it. Now for implementation reasons, memory might take a while. And so, for example, if a processor asks for the data, it may come some point in the future, right? So in this diagram, memory had a very long latency, 2 seconds. But the latency of memory, if it was stored in DRAM, which is a very common implementation of memory, can be hundreds of processor cycles. So imagine if you had a sequence like this: load from memory this address into this register, load from memory this address into this register, then add those two values. You might have to wait hundreds of cycles to actually get that data. Okay? So what can we do about that? A processor has a detail in it. So I have a processor with execution, registers, fetch and decode, and memory's off over here. What is a cache? What is a cache? You know, not this, but
a small amount of memory you can access frequently.
So if DRAM is storage for memory, a DRAM holds a lot of data, but is a storage mechanism that has high latency. A cache is another storage mechanism that can't hold that much data, but has very low latency. So if DRAM is my garage, cache is my desktop in my office, right? Less space, but much faster to access. So now we're talking about implementation of memory. A processor not only has stuff to execute instructions, it has a little bit of storage in it, a little bit of storage that's used to keep values in memory, a copy of those values to make it easier to access. Okay? So in this example, I might have a memory address space that in this case is 16 bytes, and I have a data cache that can hold 2 bytes. See that? So there's a little bit of a question of what data goes in this cache, and we're not going to even talk about it in this class very much. But I want you to just think about it as the cache is going to function of whenever it needs to put something in there, it's just going to kick the last thing out. Okay? So if you give me 1 minute or 2 minutes, I should be able to finish up on time. So imagine that this is memory. These are, memory. I'm not telling you how it's implemented. It's just an array of 16 bytes. And now I want you to imagine that a processor issues instructions to access these addresses. So there's an instruction to access 0, 1, 2, 3, 2, back to 1, 4, 1, and so on and so on. So the program's order is kind of going down this way. Okay? So when the program accesses the value, I need the value at 0, address 0, it's going to need to load some data from memory. Now here's one implementation detail that we can't get around. Caches transfer data is transferred from out in memory onto on-chip caches in the granularity of some number of bytes. That typically is called the cache line. So in this illustration, let's just say that that cache line is 4 bytes, and I have a cache with room for 2 cache lines. Okay? So when my program accesses address 0, it will bring an entire cache line, all the data for that pink box, into cache. So what happens when my program accesses address 1? The data's already there. And 3, the data's already there. And so on and so on, right? So these cache lines, these caches provide an interesting benefit. They assume that if you've accessed some data, you're going to access the data right next to it. So there's some value in reading through memory completely in the same order. Now what happens if I go back and want to access 2 again? It's already there. So they also have a benefit of when I access things over and over, it's really quick. What happens if I hit 1? Again, it's there. 1, again, it's there, and so on and so on. So I'll finish this sequence up tomorrow, but I want to end with one fun thing. This is the effect of caches. So if the data is stored out in DRAM memory, you're going to have to wait for a while. If it's stored in certain processor caches, you don't have to wait long at all. So I've made this to scale. If data is in cache, and the closest cache to the processor might hold a few kilobytes, that's how long it takes to access. A nearby cache, a little bit farther cache, a little bit longer. If data is not in cache, this is relatively how long it takes a load instruction to work. Okay? I'll end there. I'll let Ron get started, and we'll get into some details of why this is the case and the implications next time.